of those fundamental challenges and something that's really engaged our imaginations probably since the beginning of human consciousness is, are we out there? Are we alone? Is Earth it? And one of the things that we've been pursuing, of course, is it possible to not just venture to another planet, not just get there, plant a flag, and come home, but actually live there, actually pioneer the surface of Mars. And it's possible, or at least I'm going to hopefully present my argument as to why it's possible to y'all today, using microorganisms, the very same microorganisms that we think transformed the surface of the Earth so long ago, and how we arrived here today. So I wanted to start off basically like I said, the fundamental question is asking, are we alone on the planet? And it's one of those things that we've always asked. It's some of the missions that have been led on Mars and are continuing on Mars. And one of the challenges, of course, to that is if you're looking for life, beyond Earth, you're looking literally for a needle in a haystack. And so one of the things that we wanted to do was kind of flip the script on that and say, well, if life if it could exist beyond Earth, then you're at least answering a question. Instead of trying to find whether it's there or not, let's see if it's even possible, and then we can kind of engage in that sort of thing. So one of the things that we thought of was, of course, that since Mars is our nearest neighbor in the solar system, it's probably our best bet to look to see if potentially we could colonize the surface of another planet. And so fundamentally, if you think about transforming the surface of another planet, which would be, a feat of human engineering, the likes of which human history has obviously never seen, one of the fundamental things you got to deal with, of course, is you have to find shelter from the elements. So on an engineering side and material science side, you'd have to build the structure, and most likely whatever spaceship that we use to travel to Mars would probably be the same life pod, so to speak, that once it sets down on Mars, you've got a ready-built shelter right there for you on the Martian surface. So the next question is, if you're going to colonize the surface, just like our early colonists did when they discovered the New World, the secret is you can't take everything you need with you, because it's too heavy, it's too expensive. You got to travel light, and you got to live off the land. So if we're going to try to do that on the Martian surface, one of the fundamental problems you got to deal with is you got to figure out a way to create a breathable atmosphere. Mars atmosphere is nothing like the Earth atmosphere. So if you're going to have people, any critters from Earth living on the Martian surface, you got to have a breathable atmosphere. So that's problem number one. Problem number two, of course, is you have to sustain that life with food. You got to give them something that they can eat. So food production is a major issue. Of course, if we have human habitation there, all of these kinds of structures are going to require energy. You got to turn the lights on, you got to keep it warm enough for human beings to live there. So energy production, we've all probably heard about biofuels. If you have the creation of energy through biological organisms, that might be a good idea as well. And then finally, if you're living in an enclosed space, whether you're on the rocket ship heading to Mars or if you're actually there on the Martian surface, we are going to be producing waste material. And unless you want to poison your own environment, which of course you don't want to do, you got to figure out a way to recycle that stuff. So of course here on Earth, back in the day, we just dumped it. Now we're doing a much better job of recycling that waste and trying to figure out ways where we can utilize the waste in a beneficial way. So you're going to have to do all those sorts of things. So you'll notice on my slide that I've got, of those 5 problems, those 5 major problems, 4 of them are shaded in green because we think that we have a biological solution to everything that's shaded in green. And it's something that you and I take for granted every single day. Anybody who has a garden at home, has a house plant that you're going to cover when it starts getting a little cold, the miracle is photosynthesis. Photosynthesis is the secret, in my opinion, to colonizing Mars, because there are organisms on planet Earth, if we can take them to Mars, that through their natural biologic activity, they can do all of those things. They can create a breathable atmosphere. They can make food for us. They can make biofuels that we can use to energize our living space, and they can recycle our waste. So what I hope to convince you all today is, thinking about photosynthesis and how it's going to be possible to use the power of photosynthesis on the planet of Mars. Okay, so photosynthesis, fundamentally, we all probably have a pretty good understanding of what photosynthesis is. I mean, plants do it, algae do it, that's how they make their living. And one of the key ingredients, of course, we all know you got to grow your garden in the sunlight. You got to, unless you've got a plant that really, really, really likes the shade, regardless, you can't grow them in the dark, right? They're not mushrooms. So you got to grow them with some amount of sunlight. So sunlight is a key ingredient of photosynthesis. Another key ingredient of photosynthesis is the much maligned atmospheric gas, carbon dioxide. Without carbon dioxide, there is no photosynthesis. There is no life on this planet as we know it. Carbon dioxide forms the basis of the food chain. Every organism on this planet relies on photosynthetic organisms to use carbon dioxide to then make food that we can then eat. So you make a salad, or you make any kind of vegetable matter that we can utilize as food is going to be coming from carbon dioxide. So that's another key ingredient. Okay, third ingredient, which we probably don't think about all that often, are salts in the soils. So we know that we grow our garden, we have to add fertilizers every now and again. Those are fundamentally salts that when those salts are available, and this is kind of gets back to, there are a lot of principles in science that kind of follow what we call the Goldilocks principle, which is, you don't want too much of it and you don't want too little of it. So salt is essentially the same thing. In your soils, the nutrients, the fertilizers that are available to those plants, if you have too much, it can kill them. And if you have too few, they basically die of malnutrition. So if you have that right balance, you've got exactly what you need. So that's a big question of whether we have nitrogen-based fertilizers or phosphorus-based fertilizers. That's what we use every day in our own agricultural pursuits, and it's something that plants need. So that's a big question as to whether that exists on Mars. Liquid water. You guys have probably heard quite a bit lately in the news. There was just a news release a couple weeks ago about even more evidence that scientists have found evidence of liquid water on Mars. Hugely significant if we can demonstrate that beyond a shadow of a doubt, because liquid water is, of course, an absolutely fundamental and critical part of this equation. You can't have photosynthesis unless you have liquid water that can percolate into the soils, dissolve those salts, and then the plants basically absorb that water and those nutrients into their root tissues, into the cells, and then can photosynthesize, can do the magic of taking carbon dioxide and a little bit of sunlight and converting it into sugar, converting it into something that's edible for another organism to eat and sustain itself. So those are the big issues to think about. Okay, if we're going to colonize Mars, this is probably going to be the way we want to do it. So if you can grow plants on the Martian surface, there's one other added benefit as a byproduct of photosynthesis, is that plants, believe it or not, to a plant, they produce a waste product that is oxygen gas. For us, it's absolutely critical, of course, for our survival. So we get, as a benefit to this waste recycling, to producing food for ourselves, we get the benefit of our gardens essentially creating the atmosphere that's going to allow us to continue breathing in our little Martian capsule. So, an amazing amount of survivability that's granted by something, like I said, that we probably take for granted every day, or just the lowly plant on our planet. So, okay, so let's walk through it and think about this from a perspective of, okay, let's go down the checklist and see what Mars has relative to photosynthesis to see if it's even possible. So the first thing we talked about was, of course, sunlight. And as we probably all know, if anybody remembers that old show, it was an old sitcom called Third Rock from the Sun, right? That's the Earth. We are a third away from from the sun. Mars is fourth rock from the sun. So it's a little bit further away from the sun. So if you're on Mars, the sun's going to be farther away. So the amount of light you're receiving is going to be diminished, and the amount of heat you're going to be receiving on the Martian surface is going to be diminished. And in fact, it's about 43%, give or take, the amount of visible light that plants need in order to go through photosynthesis. There's only about 43% of it compared to what we see here on Earth. But that's still plenty. There are plenty of plants on this planet that can survive in very, very low light environments. So 43%, maybe not ideal, but it's certainly doable. There are a lot of plants that can handle that. Okay, so beautiful. We've got light. There's certainly sufficient light, visible light on the planet's surface for photosynthesis to take place. So let's shift gears and think instead about carbon dioxide. And carbon dioxide is an interesting situation because, and I apologize in advance for these next couple lines. I promise it's the only math in this presentation. I can't help myself. So my students, of course, would ask me, please help yourself on those. But anyway, so here on Earth, the amazing thing is, if you imagine that all of the atmospheric gases, all of the air, essentially, that we're breathing, let's assume, it's kind of easier for us to imagine these things if we start talking dollars and cents. So let's imagine 100% of all the air molecules that we're breathing is essentially equivalent to $100. Carbon dioxide, or the share of carbon dioxide in the atmosphere we're breathing, is worth 4 cents. So in our $100 budget of gases that are available to plants, only 4 pennies are available in carbon dioxide. And so plants, from that perspective, are begging for more CO2. They do great, and there's plenty of experiments that agricultural folks have done that if you increase carbon dioxide levels, that photosynthesis increases, plant production, food production, you name it, will increase. So if you do the math, we find out that there's very, very little amount of our atmospheric pressure is actually CO2. If you look at the Martian atmosphere is almost 100% carbon dioxide. It's 95%, give or take. So of that $100 budget, $95 of that on Mars is CO2. Now, the caveat about that is that Martian atmosphere is very, very thin. If all the air that we're breathing right now, if we could suck out 99% of everything we're breathing right now, that would essentially be the Martian atmosphere. Atmosphere on Mars is extremely thin. So you have this interesting paradigm where you have a very, very thin atmosphere on Mars, but because CO2 is such a huge part of it, it actually turns out that the amount of CO2 on the Martian surface is 23 times as much as it is here on Earth. So from that perspective, the availability of carbon dioxide on Mars, absolutely, the plants would absolutely enjoy if you can get them to grow under the other conditions. CO2 is not going to be a problem on the Martian surface. Okay, so shifting gears again to the nutrient argument, we talked about how fertilizers like nitrogen and phosphorus, whether they're present on the Martian surface. Well, fortunately for us, amongst the many, many, many Mars missions that NASA has conducted, that one in particular is extremely valuable. That's the Phoenix lander. And the reason why the Phoenix lander was so valuable from kind of an Earth science perspective is that they had an experiment on board where the rover literally took a little scoop of Martian soil and dumped it into a vessel of water. It was super duper high purity, I mean the purest water that humans can engineer, we put on this lander. And what they did was it measured the kind of salts that came out of the Martian soil. So if you imagine if you're watering your houseplants on the Martian surface and you're using Mars soil, that's the liquid that's basically going to come out from those soils, the salts that dissolve. And what they found is that all the concentrations, I know this is a little bit technical, but most of the salts that came out were the same kind of salts that we have in our own soils. Sodium, magnesium, calcium, that's all the stuff that's just kind of common everyday type stuff that we have in Earth soils. So no real surprises there, with the exception of this perchlorate ion, which when we found it, immediately NASA scientists thought, okay, deal's up. This actually is a very, very toxic compound. And so we thought the fact that it was present in Martian soils means that anything we tried to grow there, it would kill them outright. And they're relatively high concentrations. Now, never mind the fact that we actually did discover nitrogen in the soils as ammonia, and the Viking landers previously had discovered that there's phosphate. So the fertilizers that plants need, that we know that they need, are there. The problem is there's this toxic compound in the soil. So one of the things that I did with a number of my students was we recreated the Mars chemistry, essentially. So we ran some experiments in my lab, and we created the exact replica of the Phoenix data, the chemical replicant of Martian meltwater, so to speak, if you put water through Martian soils. And what we did was we took everyday algae, microscopic photosynthetic algae from the Gulf of Mexico. We put them in this Martian meltwater, and when we put them in, the water was absolutely clear because we only added a tiny, tiny amount of algae, and a month later, we had explosive growth. So these are humdrum, everyday, literally in our backyard in the Gulf of Mexico kind of algae that are growing in that perchlorate ion. So hugely significant, because it means even though that perchlorate, that toxic compound is there, that life somehow figures out a way to get around it, that they are able to detoxify that toxic compound. So that means, of course, that photosynthesis is possible from a chemical experiment. And this, I just want to show you guys some data. The blue line here at the bottom represents the salt that was actually measured at the Phoenix lander. And what we did in my lab was we said, okay, let's make it even saltier. So 3 times saltier, 5 times, 7 times, 10 times saltier. And you actually see that the plants actually grow even better when you have higher salt concentrations. So the good news about that is that you have to use less water And if you get a saltier solution, the plants can still grow in it really, really, really well. So that's super good news because water is going to be at a premium on the Martian surface. So if you're going to water your plants, you want to use only a tiny, tiny, tiny bit. They're not going to be bothered by that high salt concentration. So at least the photosynthetic algae. Okay, so sufficient nutrients, absolutely. The next and the real big elephant in the room is, can you get liquid water on the Martian surface? Because that's really what's going to drive all of this. And so when we look at what's called a phase diagram of water, and not to get too technical about this, but the take-home message of this is, of course, we know that if you warm water up, it becomes vapor, what's shaded in kind of orange here. Those are the conditions where if the temperature and the atmospheric pressure is just right, if it's really, really hot, you'll get vapor. If you cool the water way, way, way down, you're going to get what's shaded in blue. You'll get solid water. You'll get ice. But the sweet spot is what's shaded in green. If you have just the right temperature and just the right atmospheric pressure, you'll have water that will exist in its liquid form. And what we found, again, thanks to the Martian rovers, is that what's shaded in red here is basically the actual environmental conditions that have been measured on the surface of Mars. So the temperature ranges, the pressure ranges are all kind of interscribed inside that red box. And the cool thing about that is, even though it's a very, very narrow window, there are conditions on the Martian surface where we have that little green wedge, which means that there are locations on the Martian surface where water will be present in its liquid form, which again is a hugely significant thing. So if we can target those locations on the Martian surface, we'll know that if we water our plants, the water's not going to freeze, water's not going to boil off as vapor, but we can keep it liquid. So what type of organism can we use to do this? Antarctic cyanobacteria. Cyanobacteria are bacteria, essentially single-celled organisms that are aquatic. They like living in the marine environment, and they're capable of photosynthesis. Because they come from Antarctica, they can survive multiple freeze and thaw cycles. These are organisms that exist here on planet Earth, have high photosynthesis in very, very low light, resistant to ultraviolet radiation, so it doesn't matter that Mars has a thin atmosphere and are getting cooked by this ultraviolet radiation. These cyanobacteria might be good. If we can take them out of the Antarctic and put them basically on a spaceship headed to Mars, these are probably going to be our best bet, being able to grow in these extremely low temperatures and grow in those very, very salty conditions. These critters here on planet Earth, they're already doing it. So they're the best, I think, they're our best opportunity to use them to try to colonize the surface of Mars. So fundamentally, the next steps are to recreate the Martian environment in a very enclosed space, incubate it to see if they can actually survive, and if they grow, the next step is, of course, taking them to the International Space Station to see if they can actually grow in low gravity. Because if they can grow on Earth and they can grow in low gravity, then they'll probably be able to grow in the reduced gravity of Mars. And so we'll see where we go from here. All right. Thank you all. I appreciate it.